let's go. So page 31. So let's just call this one example, but this will be a quick example, okay? So we're going to consider beam, and in this case, I'm not going to do all the details. I'm just going to go to the results right away. So imagine that you have a cantilever beam that is one meter long. Our current system is going to be X, Y, and Z. So we're going to apply two forces. One, a force Fy equal to 100 newtons. So this will bend about the z-axis, and then I'm going to apply also a force here, positive Fz force equal to 100 newtons. Okay, so doing very simple values. And we're going to use as the cross section, the same cross section that we had last time. That way we already have the results. So we use the C section. Well, this was D, if I remember right. This was T flange, T web, D flange, and the dimensions were, let's see if I can find it. So we had D equal to 178 millimeters, B sub F equal to 58.4 millimeters, thickness of the web equal to 10.6 millimeters, and T of the flange equal to 9.30 millimeters. Okay, and basically I think on that cross section we had to calculate the stresses at 2 points that were here, point H at this corner and point K at this point. Okay, so the question here is to determine the normal stress at points H and K. Okay, so I mean, let me do it from scratch. I wasn't planning on doing it, but I'm gonna go a little bit quick. So what is the step? So for example, in the homework, something that I'm looking for, somebody was asking me last class, what I like is to see a procedure that you always solve the problem the same way, no? Okay, so what is the first thing we need to do? Some type of figure or sketch. So let's say our figure could be what? We have here Fy, Fc, both of them are equal to 100. Now, what would be the reactions you have? You have here, let's say, a Y. You might have here to be too many things on one figure. All right, so let's do figure. Let's do here case Fy only. Okay, and that way I think it's going to be easier. Remove this force over here. Yeah, I think we're going to do it that way. Okay. So we have this, then you might have here, whatever, a sub x, and you're gonna have a resulting moment m sub r. So step 2, you need to find the value of the reactions. So again, I go a bit fast. So in this case, I'm not even doing the x. I mean, you can put the x to z because it will be 0. If we do summation of forces on the y, you will have what? Ay plus 100 equal to 0, which will give you that Ay needs to be equal to minus 100 newtons. And to find the moment, we can take the moments about point A. And you will find out that m sub r plus Fy times L equal to 0, which will give you that mr is equal to minus 100. So it's minus 100 times 1. So equal to minus 100 newtons meter. All right, so we have this now. Step 3 will be to do the shear and bending moment. So in order to find the shear, I mean, we do the boosting with both of them. We make a cut on this beam anywhere over here. So we do the figure. Sorry, this is straight. This is the cut, we make it over here. Here we know we have Ay equal to 100. It's going down because it's negative. And we know that m sub r goes clockwise and is equal to 100 as well. Here we're gonna have the shear force, and this will be the bending moment. So in order to find the shear, we do summation of forces on the y equal to 0, which will give you minus v minus 100 equal to 0, which will give you that v equal to minus 100 newtons. And if we do the summation of moments about the cut. You're gonna get that minus m sub r plus m times what? Oh, yeah, plus 100x. So this will give us that m is equal to mr minus 100x, which will give you that m is equal to 100 minus 100x. I think it would be easier to look at it that way. So that if we do the shear and bending moment diagram for this structure, this is V, this is X, so this will be 1 meter. This will be the moment so maybe let's be a bit careful here. This would be the moment about which axis, so we can differentiate. This really will be mz, and this will be vy. So let me add those things here: vy, mz, vy, mz, mz. Okay, so I know I'm going a bit fast, but let me just go back again. Right now, the only force we are taking into consideration is the Fy equal to 100. Okay, so this is going to create a shear force on the y direction, but it's also going to create a moment about the z-axis, no? Okay, so we do the, so we have to do the figure. What do we know about the force on the y? It will be constant, oops, and it's equal to negative 100. I thought it was 100, so sorry for that. Here, maybe let me just change one thing, change the x-axis over here. Doesn't matter. Let's say here would be the minus 100. So that the shear force is constant. Now, if we plot the moment, what should be the moment? At x equals 0, would be 100. This is the equation of a linear function, of a line. What would be the value at the end? 0. So this is what we have. And again, this is Vy, this is Mz. All right. So now let's redo the same thing. So next, following the same procedure, we're going to do what? One figure, but this time we're going to have case FZ only. So basically it's going to be everything almost identical. But let's say we're going to have point A over here. I'll do the free body. Okay, so we're going to have A over here. This is our beam, but now we're going to have, this is X, Y, and Z. we have Fz, A sub z, and this force is going to create a moment about y, no? Yeah. So I do counterclockwise. So here, let's say this will be mr again. Doesn't matter. It's gonna. I mean, I'm just looking at the same page, exactly the same thing as the other one. 2 reactions. This time, instead of taking forces on the y, we take forces on the z. We're gonna get f of z minus az equal to 0. So az equal to f of z equal to 100. Is that correct? Yeah. And we take moments about point A. And this is going to give us what? So m sub r. And now this moment is going to create a moment clockwise. So it's going to be minus f sub z times L equal to 0, or m sub r. M sub r would be 100. So it's 100 times 1, 100 Newton meters. And again, same as before. Three, shear and bending moment. So again, it's exactly the same step as before. So I'm even just kind of recopying exactly the same procedure. So we make the cut. But this time we're gonna have, let's see, AY. So we're gonna have, so this will be, here the coordinate system will be, let's see, X. I'm gonna put well, I'm gonna change this stuff. So let me change this, X, Y, Z. So let's see how can I switch this one. I want this to be Z. So X times Y. So this will be X, and this will be Y. So I'm kind of flipping. So this will be now VZ, and this will be MY, and this will be, so what did we do with AY? It's going negative 100, and here will be the AZ 100. So once again, if we apply summation of forces on the Y, we get the on the Z. So sorry, we're gonna find the shear force on the Z. So we get minus 100 minus VZ equal to 0, which is gonna give us VZ equal to negative 100 newtons. And summation of moments about the cut equal to 0. So this will give us what? So this will be so here we need to be a bit careful because, all right. So we have MY. So I forgot to do something here. What is MR? MR is positive about the Y. So if it's positive we'll go counterclockwise. So I forgot to put it on this figure, sorry. This will be an R. So it will give us, let's see, MR, let's see if that's correct, plus MY.
Professor?
So MY, and then this one's going to create plus 100. And really, this should be X over here. So basically, we get over here that MY, I want to go to the next page, will be equal to, we should get the same as before, will be equal to, we need to be careful here with the signs. So let's see, MR here is going counterclockwise. We find positive. All right, here, I think we get, sorry for that, guys. Let me change. Yeah, this one is actually going on the opposite direction. Because what I'm trying to say, why is it going on the opposite direction? Either this one needs to go into the opposite direction, because what is the goal? At the end, this element needs to be in equilibrium, no? So the moments need to counter-react each other. So then this will give us minus MR plus MY, or MY would be equal to then 100 minus 100x again. So basically, we get exactly the same figures as before, but this time for the BZ. So again, I'm just showing all the work, but this should be done very quick. $34. So if we do this will be BZ. X 1 meter. This will be MY. X 1 meter. BC will be equal to minus 100. And this will be equal to 100 all the way down to 0 again. Okay, so basically, I broke the problem in two parts. The first part, case one, will be just we have the beam with this force. Second part, we have this beam with this force. Okay, all right. So knowing that, we need to find what would be the stresses at point K and point H. Okay, so we could use the results from last time. We can do that to double check. We calculated last time the moment of inertia to be I of Z to be equal to 11.314 10 to the 6, and I of Y 0.7022 10 to the 6. Okay, all right. And then we also found the CG, and we found the location of point H to be equal to this, position of K to be equal to this. All right. Okay, so all right, so let's do it. So what I'm trying to do is trying to show you how to do your problems, checking every single step. Okay, so I could do everything and then do the other one, but that's not what I want to show you. So we have this, we go back to our problem, this one here. And now personally, what I would do is I will go here and check with FEMAP. So open FEMAP. All right, so FEMAP, I will do here model. First thing you need to do is create some material. In this case, I use structural steel, which is 200 to the 9. Here we can put 0.3. Again, this is structural steel. We just need that. Now, we're going to use the property, same property as last time. So we have material this, element property type beam. And we know that we're going to use the same as last one. So shape. We click here on C channel. The height was given is on the page here. So the height is this one here. I'm going to use these values in meters. So the height is 178 to the minus 3. Let me put the Y up. Okay. Then the width of the top is 58.4, 58.4 minus 3. Width of the bottom is going to be the same. Thank you. 3. Thickness of the top is 9.3 to the minus 3. So thickness of the bottom is going to be the same. And the thickness of the web is 10.6 to the minus 3. So that should be okay here. Let me put, I mean, we don't need this, but I just did this, so I did the figure. So it does the figure over here, as you can see. Now, what was the value we found last time? For IZZ, what do we have? So I had it here. I think I'll just show you, but it's kind of similar to that one, no? So we had, let me go here. We had 11.314, 10 to the 6, but this would be 10 to the minus 6. Is this one here, 11.314. This is millimeters. 2 meters would be 10 to the minus 6 meters to the 4th. And the other one we had 0.0222 10 to the 6 will be the same thing to the minus 6. If we look at the FEMAP, we kind of get the same values. All right, over here. All right, you see it gives you all the properties. Okay. So we have this, we can go save. I say Y going up. Now let's pay attention. You see we have points 1, 2, 3, and 4. So let's see, point H corresponds to point 4 and point K to point 2. So maybe let's just keep 4 and 2 and eliminate these 2 here. That way we know we want the stresses at this point and this point. Y is going up, you can say okay. Gives you all those different properties for the area and so on and so on. Okay. All right. Now I need to create a geometry. So geometry, curved line. We go from 0 to 1 meter. Okay. Control A to center the image. Model. No, mesh control, size along curve. I'm going to put whatever you want, 20, can put 10. Deal. Now mesh geometry curve. So we're going to mesh with this property. Now it's going to ask us for the orientation. I put the Y going up. I'm going to show you what does that mean. So it means this is going up. Okay, so why am I doing that? Because I want to make sure that the beam is in this orientation, okay? These edges could be on the other direction, no? Or this beam could be actually rotated 90 degrees. But this is the way we did the calculations, all right? So I think it's F8, XY, okay. Model, constraint, nodal. I'm gonna come to here, and this is fixed. Okay, so I'm gonna do file, first this would be model load Not all. I come here and I'm first going to do case one. This will be just 100. All right, now we can call this one file, save as. Desktop will be again my model one. Doesn't matter. Let me remove this. I will just see the line. All right, so that's it. We run this. Okay, so we have this figure. We go to F5. We did that already on the other video, so that's why I'm going very fast. We want to look at the shear diagram. We look at 3018. We get the constant value of 100, no? Okay, if we do the same thing for the bending moments, it's 3014. We should get the from 100 to 0. Okay, so now F5, let's look at the stresses. So this one from the stresses will give us what? So let's see. I remember which one it was, but it was points 1 and 4, no? I don't know which one. Point 1 was what? K or H, remember? Oh, so we need just point 2. So why? I thought it was only, okay. So point 2, point K was point 2 in our cross section. What I'm trying to say is this. When we came here to the properties, this is point K. For us would be point 2 and point H will be point 4. Okay. So if we look here, okay. So let's do F5. So from here, we'll see that point 2 will be so point 2, I don't know, that was point K. Will be 7. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So 0.7866. Can you read or not? I have a hard time here. But anyway, what I was trying to say here is that we have this calculation, and in order to save some time, I created this file over here, which basically I use the moments from the FEMAP. We know the moment is just the force times the length. I copy from the notes the locations of the points, okay? And then what I did over here, you see, initially I don't put any sign, okay? But let's just do it using common sense, like we have been doing last time. So we have this cross section here. This is a cross section, and we use first Fy. So this is with bending up, no? So this is bending up. The top will be what? Or the bottom will be what? Remember how the cross section is. So if it's moving up, H should be in compression and K in tension. Yeah. All right. I hope you see that, because forget about the sign. If this is bending up, this is going to curve like this if you want. Okay. So the H will be on the part that is this part of the hand on here, and the other one will be over here. So it will be in compression. And if it was reversed, would be the other way, no? This side will be in compression, this side will be in tension. Okay, so just picture that. So basically from here, we could say that using the calculations, I will give you this file over here, or we can write it down now. Let's write it down and then we'll find out. Just the matter file. Okay. So let's come back to this page. And now let's just look at, let's say here, 1, 2, 3, 4 stresses. So first we're going to look at case Fy only. So Fy only, we're going to have sigma of, it doesn't matter, H sigma of K will be equal to what? Will be mz times y of H divided by Iz, and this will be mz y of K divided by I sub z. So we just said that this is this way, so the force is going to make it bend that way. So K should be in tension, H should be in compression. Okay, so let's see if that's what we get. So K, let's say here will be tension. But again, that's why we are doing this both ways. We can check. All right, so if we do the MATLAB calculations, that give us what? I mean, maybe I put the signs here. So I put already the results. Fy is 7, so 7.8664 10 to the 5. 7.8664 10 to the 5. And of K is the same thing, 7.8664 10 to the 5, and this should be pascals. All right, so this is the result we have. So this is point what? So we said this is K is 0.2, H is 0.4. So we come here. Here we have at 0.2. What do we have? Positive. This will be 7.8663 10 to the 5. Close enough, no? I mean, we can make more close if you refine this. Now, if we look the same thing at 0.4, we should have the same thing but negative at 0.4. Hopefully we get the same thing with a negative value, compression. Okay, so we check the hand calculations with our problem. So let's save this one, save. Now, let me do file, save as, model 2. Save, and what I'm going to do, I'm going to delete the results. I mean, I could do everything on the same figure, but if it gets more complicated, you're going to get lost. So I do this, delete, model, load. And basically, I do the same thing again, model, load, nodal. But this time, I'm just going to apply the force on the Z, which is the 100. Okay, I'm going to skip the part of doing the shear and bending moment diagrams. Okay, I'm going to go straight to the stresses. Oh, I first need to run. Okay, so it looks like it's finished. Results here. This gives us at 0.4. So whatever, this gives us minus 20 point whatever. Let's see what we get from the hand calculation. So let's go now. Case FZ only. So what would that give us? That will give us sigma H will be equal to my times ZH divided by I sub y. Sigma K should be equal to my Z sub K I of y. This value of ZH, ZK, we found them last time, okay? So we don't need to put them. I mean, those values were given in this page over here. All right. All right, so again, we have this cross section. So now this is bending about the Z. So this is now, you are pushing in that direction, no? Yeah. So what would be H okay? Try to think it would be tension or compression. H should be in compression, I agree. And K should be in tension, no? Okay. But again, let's see what the final element will give us. So this will be 0.4. So 0.4 for us is point H. We say that point H needed to be in compression, no? What do we get? A negative value, which indicates what? Compression. What is the value? 20.86.526. So in order to save some time, I did the same calculations here in MATLAB. What do we get? 20.825 10 to the 6. So kind of similar. So let me just copy down one. So this should be H is 2.0825 10 to the 6 pascals in compression, and K is 6.229 for 10 to the 6 pascals in tension. So this is tension. Compression. So this is the two results. So let's go and check with the FEMAP. We did check this one. Let's see if we get this one in tension, about 6.22294 10 to the 6. So we need to come here. We did 0.4. We need to do 0.2. Come here, 0.2. 6.229957. Okay. All right. So obviously the problem we are solving is not one at a time. Is both at the same time. Okay. So if we need to do that by hand, what will you do? So the only thing you need to do now is combine both of them. So let's say case Fy plus Fz. What should you have? You should have sigma sub h will be equal to the, so let's say here will be mz, if I put the equation, y sub h divided by I sub z plus, I mean, I don't know about the values, m of y, z of h, both of them are negative, I of y. So let me check if there's a change in sign. So both of them should be in compression for what we look at. So this will give you a value. And then the sigma sub k will be exactly the same thing over here, but m of y, m of z, y of k, I of z, plus m of y, z, oops, z of k, I of y. So if I do that into the final element, let's say I take this one, file, save as model 3, save, so I can just delete the results. Okay, I just need to add the force on the y, model, load, nodal. I pick this one, I add the 100 Newton force on the y. Okay, cancel, run. Okay, this is finished. We go to the results. All right, so let's see what we get from the MATLAB. We get here that the point at H is 2.8692 at point H, 2.8692, 10 to the 6 in compression, so pascals. And at point K is 7.016, 10 to the 6 pascals in tension. All right, so basically that's what I wrote over here. Let's see what the FEMAP will give us. So here, what do we get? 7.016593 in tension at point 2, and point 4 will be 2.873 instead of 2.8692. All right. So what is the logical behind all this stuff? There is no excuse for you to do it wrong in an exam or homework, no? Yeah? All right, so at the beginning of this section, we said that we had two types of stresses. One, the normal stresses. So we said normal stresses. And these ones were called because if we had a structure over here, and this is the area, the force was normal to the cross-sectional area, no? And then we call the other one tangential stresses, but I think they will have a different name. In this case, the force was tangential to the surface, okay? And basically, this is, so tangential stresses is the same thing as shear stresses. Okay, so again, I'm not gonna do the derivation because that should have been done in solid mechanics, but shear stresses in a beam so if you have a beam, I just do a general beam, okay? You can do any load that you want. Let's say it has a very complicated loading like this. Doesn't matter, okay? So we did the shear and bending moment diagram, okay? We did the shear bending moment diagram. So here we say the shear forces, which basically means those V that we calculated in the beam cross section produces shear stresses. So I'm not going to do the derivation. Again, that should be from solids. And anyway, if I give you derivation, you're not going to, you might understand it the way I do it, but you're never going to redo it. So it can be shown that the shear stress equation, and I hope you kind of remember this one, is V times Q divided by I sub T. Does that equation look familiar? Hopefully it does. The same thing we had for the bending moment, My divided by I. Okay, here's this. Okay, on this figure we have V is the shear force. I'm going to start by the easy one, is the second moment of inertia, or moment of inertia per second. Q, since will be our first moment of inertia. And T is just the thickness. So why do we have shear? I mean, I'm not going to do the derivation, but if you do the figure of this, I mean, let's say you have, this is a piece of this beam. Okay, if we make a cut over here, oops, it's not too good, my figure here, but it doesn't matter. If you make a cut over here, you agree that because the deformation of this plane here is not the same one as the deformation, let's say, of a plane on top over here, yeah, it will induce shear, because what is shear? We have the contact between two different surfaces. Okay, so this surface here will have some type of movement with respect to the other one. Okay, so in order to have shear, you need to have contact between two. So what should be the shear on top of the cross section? Is that one having any friction with another surface? No. Okay, so the shear on top should be zero, no? And the shear at the bottom should be zero. Where should be the shear maximum? Probably in the middle, no? Yeah, is where you have more surface rubbing against each other. Okay, so basically, let's see if we can get that kind of results using the math. So let me give you some equations here. I mean, if you want, let me do a figure here so you will understand. If this was a rectangular cross section, I'm sure you derived in solids that the shear distribution will be like this. So basically at the top and the bottom will be zero, just like we just mentioned, and in the middle, it will be maximum. And this is for the reason I told you, because at the top, it will be no surface, the Q will be zero, and at the bottom, the Q will be zero. All right, and the mathematical expression for Q is integral of y dA, and the expression for y is y dA. So this one is not a big deal because we already calculated. All right, this one is generally the one that gives you a hard time. Okay, so let's see what this first area moment of inertia is. Okay, so Q, first area moment of inertia. We know the complicated equation for this one is y dA, but there's an easy way to calculate that one. If let's say you have a cross section, that is this way, you calculate the location of the neutral axis. Okay, so I'll give you the easy way to do it. So what is Q? So Q equals to Y dA will be equal to the area. So in this case, let's say this could be the area here, A, times the distance from neutral axis to center of gravity to CG of area. So basically that distance over here. Okay, or if you want, Q will be equal to area times Y bar. If you want to call it this one, let's call this one then Y bar. And this will be Y. So this is Y bar over here. And I'm pretty sure this is the way you calculate the Q in solid mechanics. Okay, so before we do a problem about shear, I'm going to give you some general comments, but which are important. Okay, so let's say you have a structure that has a shear force acting on a area A. An easy expression to find the shear is to say that the average value here will be equal to what? Will be equal to the shear force divided by the area. Okay, now, so if I needed to plot this shear distribution throughout this cross section, it will probably look something like this. Everything is constant. However, if we use the equation, this equation here, what you get, so we use tau equal VQ divided by IT. What you actually get is something like this. Okay, and I want you to notice that there is a big difference with respect to the maximum value. Okay, so in here you can actually say that, I mean, it is exactly that for a rectangular cross section, but I'm going to say more or less is 3/2 of tau average. See, tau average, tau max. Okay, so why is that important from the design point of view? It's because let's say you need to do the design of a structure that is going to break in shear. If you use this equation, what are you doing? You are underestimating the load by how much? 50%, which is a lot, no? Yeah. So you see here, if you want the area, here should be the same than this one. But since this one is like an hyperbola, the maximum value would be much higher than this one, even though the area might be the same, no? Okay. So in the design, you need to be careful. And the other thing that I want to mention, which is important, and a lot of people do that mistake, is that the equation tau equal VQ over IT is only valid for cross sections having parallel walls. And this is something they never teach you. So for example, this is valid for what? So let me ask you here, tell me which one will be correct or not. I do multiple ones. So let's see. Will this expression be valid for this one? Are the walls parallel? Will be valid for this one? Why not? This one is parallel to this one, no? Okay, if you make a cut here, whenever you make a cut, it will be parallel. Will it be valid for this one? Obviously, because we just use it. So now, would it be valid for this one? For this one, it will not be valid because when you make the cut, the walls will not be parallel to each other, no? Okay? So be careful with those things. Even though people use this one to approximate this one, okay? All right, so what time is it? Still have 20 minutes. All right, the other thing, another comment, but this is also true for the other one. All right, let me put it here. So the equation VQ tau equal VQ over IT is only valid for thin structure. So basically that means when the length of the structure is much higher than the thickness. So what I'm trying to say is that if you have a beam, it doesn't matter what is the boundary condition, is that the length here is kind of always much larger than the depth or the thickness of the cross section. Yeah. Okay. So really I'm going to tell you something which is true, is that all the structures that you learn, including this class, is really only valid for structures that are much longer than depth, okay, or thick. If you have something that is very short and very thick, okay, or you have something which is about the same value, these equations are not valid anymore, okay? And try to think about that, all right? If you have a structure that in order to break it, you need to do this. That structure will mean what? You're going to break it in what? In shear or bending? In bending, no? But if you have something, and generally something when it's long and kind of thin, you try to break it like this, no? But if you have something that is really short, how do you try to break it? You generally try to twist it, no? In order to break it. Yeah? So that would be more, you apply a shear, no? Okay. So, but since almost all the structure basically are designed, if you look at the beams of the buildings that are building right here in campus, they are long compared to the thickness, no? Okay. If you look even at these tables, they are long compared to the thickness. All right. All the theory we're trying to teach you is the one based on this type of structures. But really, if you have something designed, something that is very thick and very short, these equations are not 100% true. Okay, just want to let you know. Don't think that everything can be used for every single case. So let's start one example. I don't know how far we're going to make it. Example. In this case, I'm not going to redo the whole problem to give you a load. Okay. I mean, actually, I could. Let's say you have, really should not matter, but let's say you have this beam over here. Doesn't matter the length. You can put any length, L. But let's say there's a force over here of 12 kilonewtons. So I'm not going to redo the analysis, but let's say the cross section of this one will be what? Will be like a T cross section. So again, I'm not going to do the figure, but if you do this here, what should be the shear diagram? How will the shear diagram will look like? Probably going to have here. I mean, if this is going up, what should happen over here? Should have a force on the opposite direction equal to 12, no? Okay, so we could say that this is a shear force over here, V equal to 12 kilonewtons. Let's change the units because I have, sorry, let's say this will be 12 kips instead of newtons because I have the dimensions in inches, even though I could have changed them to centimeters, should not matter, but. Okay, and let's say that the width over here, this will be 12 inches. That distance here is 6 inches. So obviously this is not to scale. The thickness of the top flange is 3 inches. And the thickness of the web is 4 inches. Okay, so the question here is to determine the shear in the flange and the web. So basically on the cross section, in the flange and the web. Okay, so the first thing we need to do is to find the location of the neutral axis, that will be located at the CG location. So basically, if this is, I don't know, you want to call it Y and X, okay? I mean, do we need to find where is the Y location? Y location will be right in the middle, no? So the X location will be right in the middle, sorry. What we need to determine is what will be the Y location, okay? At which height, okay? So let's do that. So in order to do that, let me write down here the equation. So I gave you that in order to find the CG, you can do the CG of each one of the parts divided by the total area. And in this case, I can break this structure into, let's say, the top flange and here the web. So let's say one part will be this one here. One. And this will be two. So now what we need to select is from where are we going to start the calculation of Y. You can either start from the bottom or you can start from the top. Okay, you can start from whatever you want, but the easy ones will be either the bottom or the top, no? Okay, here, since I have the results, my result starts from here, from the top. Okay, so I go to the next page. So basically, if we select the red area, what is the area? What is the area of this one? I mean, let's first start. What is the Y? What is the Y sub 1? The Y sub I of this cross section. What is the thickness of this one? Is 3 inches. So the Y will be at 1.5, no? So it will be 1.5 times the area of this one will be what? 12 times 3. Plus now the center of this one will be where? So it will be, if this is 3 plus 6, 9. But this is a little bit tricky. So what would be the distance? Will be 3 plus 3, no? This 3 plus half of 6 is 3, no? It will be 6. And what is the area of this one? Will be 6 times 4. And the two areas are equal to what? 12 times 3 plus 6 times 4. So if you do these calculations, you get that Y bar will be located at 3.3 inches. Okay. So now what we know is that, okay, if I do the figure here again, we know that the neutral axis is located at 3.3 inches. Okay, so now that we know that, let's calculate the moment of inertia of this cross section. So this will be what? If we calculate about the bending, so here we calculate what? If we look at the bending, this force F will produce the bending to go up and down, no? So it will be about which axis? should be bending about X. Yeah, I changed it before. Remember was Z, no? Now it's X because this is the one. So really, I mean, you don't have to put it, but if you want to be accurate, what we're going to calculate here is the I sub X about the neutral axis. So remember, we use the parallel axis theorem. So let's first do this for this one over here. For one, what would be the I for this cross section? 112 times what? The base, which is how much? The base is 12. Yeah. So 12. What is the height? It's 3 to the cube. But now what do we need to do? We need to use the parallel axis theorem to move it from here, the center of this one, to this one, no? Okay. So let's first do the area. So the area is obviously the same as before, 12 times 3. Now, what is the D? What is the distance? So that distance will be what? 3.3 minus 1.5. You see what I'm doing here? Okay, I don't want to add too much to the figure. And this is squared. So this is for 1. Now, 2, we say will be this one here. What will you have for 2? Will be 112. What will be the base for this one? 4. And the height will be 6. Perfect. 6 cubed. So the area of this one will be again 4 times 6. And now we need to move the center of this cross section. So let's say somewhere over here up to this one. So what could be that distance? Would be, so let's say if this is 6, or from here to here is, let me look at the figure again. Let's say we have 6. So you see this is 6. Yeah, so it should be 6 minus 3.3. You see that? Okay. So this could be, I mean, you can look at it differently, but this should be equal to 6 minus 3.3 squared. Let me check. Look at my notes. Yeah, I have the same thing. So if you do the calculation here, this will give you that I sub x is equal to 390.6 inch to the 4th. So again, you don't have to, but if you want, what could you do in order to check this? You could go to Nastran and just introduce the value for the cross section, and or go to CATIA and do it. No, both should give you that. Since we have about 4 minutes, and I'll probably stop over here. Let's go see very quick if FEMAP will give us the value. So let's see FEMAP here. So file new, and I will stop over here. Let's see model properties new, element property type. Let's see, we can do that very quick. Okay. Shape. What is this? This is a T section. See, we have T sections here. T sections. So what was the width of the top? 12. What is the keyboard here? So 12. What is the, no, that's the height. Sorry, the height is, so width of the top 12, you're correct. The height is 9, no, if I remember right, 6, 9. The thickness of the top is 3. Correct me if I'm not. Thickness here is 4. We put in the y on top. So what do we get? I here, this is z. For us is x, 319.6, no? You see it right here? Okay. If we need it, if this was bending also on the other direction, what would be the I sub y? We can calculate it, will be 464, no? But again, how long did it take you to do this? Not even a minute, no? And you can check your result. All right. So you see, I'm not even saving it. I'm closing this. I don't want to save anything. Don't care. Okay, so we stop over here for today.